All right, so there are two parts of 5.6. The first part will just be focusing on forming polynomials. So if we have some root information or zeros, same thing. If we know some of that, then we can work backwards and figure out what the polynomial was at the beginning. Okay, so let's start with a definition here. We've dealt with imaginary numbers before. Here's the usual format for it, a plus bi. The complex conjugate of this complex number, which we're using z as the variable for it, is this, symbolically. It's just a z with a little line over it. So if you see z with a little line over it on the homework or in Math Excel, it's just asking you for the conjugate. And what that means is you literally take the imaginary number, all of it, and just take the opposite of the imaginary portion. So if you see plus a number, bi, you're going to just switch that so it's minus bi. It's very simple, okay? So, for example, this first problem here, the conjugate, if we have 3 plus 4i, switch the imaginary so it's opposite of what it is now. Now we have 3 minus 4i. Pretty easy. The conjugate of w would be now opposite of minus 2i is positive 2i, so 9 plus 2i. Again, all we're doing is taking the opposite of the imaginary term. Okay, here for c, the opposite of the imaginary term would be negative 5i. For y, the complex conjugate, here there really is no imaginary term. I mean, we could write plus 0i, and then it would be negative 3 minus 0i, but 0 times I is nothing. So here's your complex conjugates for these 4 problems. Okay? So that's a little bit of background that you're going to need going forward. All right. Turn the page. And now we have the conjugate pairs theorem. Okay? You probably noticed this already, but now we're going to formalize it. When you guys use the quadratic formula to solve quadratics, you probably noticed a lot of the times that solutions were something like x equals 1 plus or minus 3i over 2, let's say. Well, that's not a coincidence. Look at what we have in here. If we actually wrote them out separately, this is the same as 1/2 plus 3 over 2i, or 1/2 minus 3 over 2i. Look at the relationship. These are complex conjugates. Okay? And this is exactly what the conjugate pairs theorem says. It tells us that if we know a complex root, let's say a plus bi, and we know that's a 0, then automatically its conjugate, a minus bi, is going to be a 0 also. Okay? So let's look at example 2. Again, I think you guys will like these first few problems because it's not very much work. It's just knowing how to apply this theorem. Okay, so with degree 4, we can expect, hopefully you remember, but at most 4 zeros. Currently they have 1 is a 0, 4 is a 0, and 2 minus I is a 0. That's 3. Well, there is a fourth, because automatically, if 2 minus I is a 0, the fourth root, I'm going to call it r sub r4, would be the conjugate of 2 minus I. So that would be 2 plus I. Okay? Degree 6, let's see what happens here. So negative 5 is good, 9 is good. Here we can do the conjugate of I, which is negative I. So that'll be the 5th root, since we already have 4 of them. Let me rewrite that. R to the 5 is negative I. And now we can also take the conjugate of this last number. That would be negative 8 plus 5i. So here are the remaining roots for these two problems. 2 plus I for the first one, for a total of 1, 2, 3, 4 roots. And here we had two other ones based on the conjugate pairs theorem for a total of 6. Okay, and just again a reminder, the conjugate only changes the sign of the imaginary part. You're not doing the opposite of everything. It's just the I portion. So negative I becomes positive I. Negative 5i becomes positive 5i. Okay? All right. Last. And this is the part now that you have to be really careful with how we're going to do this, because there is a little bit of algebra involved, and anytime there's a lot of algebra, it's easy to make a little mistake somewhere and then everything gets thrown off. So here we're forming a polynomial, and let's just say with the leading coefficient a. So f of x will be a, and here's what I know. 1 is a 0 with the multiplicity of 2, so that translates to a factor of x minus 1, but since the multiplicity is 2, that's going to be squared. Okay. And then for the second part, we have 2i is a root. Okay, so then that means x minus 2i is a factor. But using the conjugate pairs theorem, not only is 2i a root, but negative 2i is also a root. So then we write down the factor, which would be x minus negative, or x plus 2i. And then now we are going to, for these problems in this last section, we are going to multiply everything out and write it in standard form. So we're going to have f of x equals a. And now if it helps, okay, write down x minus 1 twice, because you're going to have to FOIL it out. And also a tip for when you're multiplying. Remember, you can multiply in whatever order you want. Like you can do these two, and then these two, and then multiply those. You could do these two here, those two there, and then multiply those. Or you could take these two times that one, and then whatever that is times that one. But here's the easiest thing to do. When you have imaginary numbers in your factors, you always want to group, like multiply these two together, because usually that's going to be easier than doing it the other way. Okay, so these two we're going to multiply together. So let's go ahead and multiply these other two together as well. Okay, so if you FOIL or distribute, whatever you want to call it, I'm going to show the work step by step the first time. You're going to get x squared minus x plus 1. Okay? Now, look at this. And if you don't recognize this, again, I'll show you step by step. But here, this is a difference of squares pattern. It's very similar to like, it's like multiplying x minus 2, x plus 2. If you guys remember when we multiplied those, we always got two terms. The first term squared and then minus the last term squared, x squared minus 4. Because if you FOIL, or multiply and distribute each term, you get x squared plus 2x and then minus 2x minus 4. The middle terms always cancel when you have the exact same terms, just one is minus and one is, I'm sorry, the exact same factors except one is minus and one is plus. Okay? So, again, I'm going to do this one step by step, but you'll see what I'm talking about here. So x times x is x squared. X times 2i is going to be 2ix. And now we multiply negative 2i with x, so negative 2ix. And then negative 2i and positive 2i make 4i squared. And if you remember, I squared is equal to negative 1. Okay, so let's see what we have. X squared minus 2x plus 1. These middle terms cancel. So then it's just x squared. Negative 4 times negative 1 would actually make this into a positive 4. Okay, now we're almost done. Okay, now we're going to have to multiply this factor with this one. Okay, and again, I like to say just distribute every term instead of FOIL, but that's what we're going to do. We're going to take x squared first and distribute that to x squared and 4. So that's going to give me x to the 4 plus 4x squared. Now I take the negative 2x and distribute it to every term. So that'll be negative 2x times x squared, which is negative 2x cubed. Negative 2x times 4 is negative 8x. Okay? Now we just have the 1 to distribute. 1 times x squared is x squared. 1 times 4 is 4. And now we just combine our like terms. Don't forget we have that a in front of all of this. So we have a, x to the 4. Looks like we have a minus 2x cubed. If we look at the squares, there are 2 of them. 4 and 1 make 5. And then we have minus 8x plus 4. Now, I'm not sure. I think most of the time in Math Excel, they say leading coefficient equals 1. If that's the case, then this is what we're looking for, just this polynomial in here. Okay? All right. If you need to pause or have me re-explain something, feel free. Rewind it, try it again, whatever you got to do. Okay, one more problem. And then, again, I'll go through this one slowly, but I want you guys to try to remember this difference of squares thing and how the middle terms end up canceling, because that's going to help you. All right? Now, if 3 minus 2i is a 0 or a root, that means 3 plus 2i is also a root. Negative 1 has a multiplicity of 2, so that takes care of the other root. So let's write out the factors. And let's just assume here that a is 1. Okay? If 3 minus 2i is a factor, then x minus the quantity 3 minus 2i. I said that wrong, sorry. If 3 minus 2i is a root or a 0, then x minus the quantity of 3 minus 2i is a factor. If 3 plus 2i is a root, then x minus the quantity of 3 plus 2i is a root. And now we have negative 1 is a root, so that's x plus 1, and multiplicity is 2, so that's squared. Okay, now we're going to multiply things out, but here's where you want to do a very clever thing. Okay? It'll help you multiply these goofy polynomials out. You're going to take this and you're going to rewrite both terms. And what you're going to do is distribute this negative. So you get x minus 3 plus 2i. Same thing here. Distribute the negative. For now, we'll just leave x plus 1 alone. And now here's the final piece. After you distribute the negative, put parentheses around the x minus 3, the first two numbers here, and consider this its own term. Okay, and the reason I'm saying to do that is because now this is almost like having a plus b and a minus b again. It's that difference of squares pattern. Remember, when you multiply a plus b with a minus b, you get first thing squared, first term squared, minus second term squared. Well, here, my first term is x minus 3. So it's going to be x minus 3 squared minus the second term squared. So that'll be 4i squared. Okay, and then if you FOIL that out or distribute, that's going to be x squared plus 2x plus 1 over here. And now we're getting closer. Multiply this out or distribute. You get x squared minus 6x plus 9. I squared is, again, negative 1. So that is actually going to become plus 4. Combine some like terms. And now you got a 3-term, whoops, that's a 2, not a 3. You got a 3-term polynomial that you have to distribute with a 3-term polynomial. So it's just like FOIL, but you have to distribute every term. So I'm going to start with the x squared. X squared distributed to the second factor is going to be x to the 4. X squared times 2x is 2x cubed. X squared times 1 is x squared. And so that's distributing the x squared. Now I'm going to distribute the negative 6x. So negative 6x times x squared is minus 6x cubed. Negative 6x times 2x is minus 12x squared. And the negative 6x times 1 is minus 6x. And now I just have the 13 to distribute. Positive 13 times x squared is 13x squared. Positive 13 times 2x is 26x. Positive 13 times 1 is 13. It looks very long, but we can combine some like terms. X to the 4 is good. There's nothing else to combine with that one. But I see a couple of cubes. 2 minus 6 makes negative 4 cubes, so negative 4x cubed. We have x squared here, minus 12x squared, that makes negative 11, plus 13, that makes positive 2x squared. Just combining like terms here. Now we want to find the x's. Here's an x, minus 6x, and then positive 26. That adds up to positive 20x. And I think I've gotten everything except for this 13. So here's our final answer. X to the 4 minus 4x cubed plus 2x squared plus 20x plus 13. Whew, okay. Just pay attention in Math Excel or on your homework if they say to use a certain coefficient, like maybe they say use a coefficient of 2. Well, then you would put a 2 in front of this whole thing and double it all. So 2x to the 4 minus 8x cubed and so on. Okay? All right, so that's the end of the notes for today for the first part of 5.6. You can use the rest of the time to start working on Math Excel. You could probably get half of that 5.6 section done now. And if you're done with that, you could also start working on 5.6 in the packet. All right, I'll see you guys tomorrow.